Today we're going to talk about graphing the parent function for the rational family. This is our last new family. This is the only one where you're going to have x in a denominator. So every single rational function will be a fraction. I know that you're so excited to hear that. So our standard numbers for the table for the parent function are between -2 and +2. When I plug these in, I'm going to have to put them in the denominator. So 1 divided by -2 would be -0.5. 1 divided by -1 is -1. 1 divided by 0 is a little bit of a problem here. There's a big difference between 1 divided by 0 and 0 divided by 1. If 0 is in the numerator, the answer is 0 no matter what number is on the bottom. If your 0 is in the denominator, it's like asking for you to take a number that's on the top. So take 1 and divide it into 0 parts. You can't do that. You can't take something and divide it into nothing. So when you have this situation where you have 0 in the denominator, it's going to be undefined. And what that means is that our graph cannot exist when x is equal to 0. So that's going to come up, I'm going to put undefined here. And that's going to create something new that we haven't talked about yet when we get to our graph. 1 divided by 1 is 1, and then 1 divided by 2 is 0.5. Okay, so that undefined portion, what that's going to do is it's going to turn into something called an asymptote. So the first thing I'm going to do is I'm going to draw, remember that this is your x-axis, this is your y-axis. So if I want to draw the line x equals 0, it's a vertical line, and it has to go through the x value of 0. Okay, so that's one of our boundary lines. And it's actually, since it's a vertical line, we would say that it's x equals 0. So now if I plot these points, let's see, -2 and then -0.5 would be about here. -1 would be about there. And then 1, 1 would be here. And then 2.5 would be about there. So what's going to happen here, since we had this boundary line where x cannot, our graph can't go there, our graph can't cross through where x equals 0. We also have one for our y's, and this one is not as obvious. But if you look at our equation, the numerator is 1. The only way to make a fraction equal to 0 is if 0 is in the denominator. But if 0 is in the numerator, but our numerator is 1, and that's not going to change. So what that means is that our graph also will never ever equal 0 for the y value. So just like we had a boundary line at 0 for x, we're also going to have a boundary line at 0 for y. And that's going to be the line y equals 0. So I have two boundary lines, and those, like I said, are called asymptotes. So what our graph is going to look like, we haven't actually talked about that part yet. Our graph is going to look like this. It's actually going to be two pieces, two separate curves. And the reason we have these two pieces is because we can't cross through those boundary lines. So for our domain and range, these are actually going to be not terrible. Let me go ahead and write down our asymptote. So we have x equals 0 and y equals 0. And I'm going to put down here that these are boundary lines that our graph cannot cross. Okay, so for our domain, the only x value that poses an issue to us is 0. That's the only one where if I try plugging it into the equation, I will not be able to get an answer. So here's how we're going to write our domain. We're going to say that the domain is all real numbers except x cannot equal 0. So you write x equals 0 and then through a slash through the equal sign, and that means that x cannot equal 0. We're going to do the same thing for the range. All y values work. The only thing we cannot get our equation to equal is 0. So we're going to say all real numbers except y cannot equal 0. And make sure you use x for domain and y for range. Now the end behavior, we have a ton of stuff going on. Up until this point, at most we've had 2 arrows, and so we've had 2 end behavior statements. we are still going to have two end behavior statements, but we're only going to be focused on the ends that go toward the left and to the right. I'm not so concerned about the arrows that are going up and down. But that means that something's going to change when we look at our end behavior. So I'm still going to be looking at when x goes towards infinity to the right and negative infinity to the left. But now instead of our y's going towards infinity, our y's are leveling out. They're basically flattening out and almost becoming the x-axis. So what we're going to say is as x goes to the right, y gets really close to 0. And as x goes to the left, y gets really close to 0. And those will always be your answers. We're never going to talk about the arrows that are going up or down, just the ones that go towards infinity and negative infinity, like we've been talking about this whole time. When we're not talking about the parent function, it's good to know kind of what the rules are. So to find the domain, we're going to set the denominator equal to 0. And the denominator will always have the x in it. So whatever expression has the x, that's what you want to set equal to 0. And then you want to solve it for x. And that number is going to give you your exception. So when you say your answer, you'll say all real numbers except, and then you want to write x doesn't equal, and then what you're going to plug into that is whatever you get from this answer right here. So that's going to go inside your domain. To find the range, you want to find your k value, and then your range will be all real numbers except y cannot equal whatever your k value is. And then like we just discussed, your end behavior, your y's do not go towards infinity. So your y's don't go towards infinity. You still have one x going each way, but your y's will both go towards whatever your k value is. In our parent function, it went towards 0 because 0 was our k value, but that can change if it's being shifted up or down. And then those asymptotes are a place on a graph where the domain or the range is undefined. And then in order to graph it, you're going to use a dotted line. So you don't want it to be a solid line because it's not actually part of your graph, but it does need to be represented on your graph as those boundary lines where your graph can't cross. And every rational function in this unit that we're going to talk about will have two asymptotes. For these first few problems, we're going to just identify the asymptotes. So what I want to do up at the top here is write down our standard form that we've been talking about, which looks a bit different than the other ones because so far our x minus h has always been inside of parentheses or absolute value or radical, and now it's actually in the denominator of a fraction. So it looks a little bit different. And then your a number will be on the top of that fraction. Normally it's 1, that's what it is in the parent function, but that number can change. But the good news is that a does not change, it doesn't have an effect on asymptotes. So for these problems here, we can pretty much ignore any numbers that are in the numerator of the fraction. All right, so let's take a look at number 1. Remember that we're going to have two asymptotes. We're always going to have an x equals and a y equals asymptote. And pretty much whatever our h value is going to be our asymptote for the x value. And then whatever your k number is will be your asymptote for your y value. So we're going to do these one at a time. So for the x equals, I want my h value. This is my denominator right here. I don't have an h value. So remember, when something is missing, it means it's 0. So that means that this graph cannot equal 0. And essentially all you're trying to think about is what number, if you plugged it in for x, would make your denominator 0. Because you can't divide by 0, so that means that would be that x value would be impossible on our graph. So if I plugged in 0 for x here, it would make me divide by 0, therefore that's my asymptote. And then for my y, I set it equal to my k value, which in this problem is 5. For number 2, for my asymptote, for my x value, I'm imagining if I plugged in a number for x, what would make it 0? And in this problem, it's 1. And if it's hard to see that one, you can take your x minus 1 and set it equal to 0. And then if you added 1 to both sides, you would get that x equals 1. So x equals 1 is my first asymptote. And then my second asymptote, my y value, my y asymptote is going to be my k value. And since there's nothing there, it's like there's a plus 0. So my y asymptote would be y equals 0. For number 3, I would have x equals 0. There's nothing to solve. So if I plugged in a 0 for x, I would divide by 0, end of story. And then same thing for my y value. There is no k value, so it's a 0. For number 4, my x asymptote, if I take this and I set it equal to 0, x minus 4 equals 0, and then I would add 4 to both sides. So I would get x equals 4. So that's going to be my vertical asymptote because x lines are vertical. And then my horizontal asymptote, which because y equals lines are horizontal, is my k value of 6. And then the last one I'm going to do here is number 5. If I plugged in 0 for my x value, I would be dividing by 0. So anytime that there's just an x, so you don't have x plus or x minus anything, your vertical asymptote is always going to be x equals 0. And then for my horizontal asymptote, I take my k value, which is negative 2. The first thing I like to do in these problems is figure out the asymptotes. So remember, there will always be 2 asymptotes, a vertical and a horizontal. The vertical asymptote will always be x equals, and the horizontal will always be y equals. So it's the opposite of the axes. And the reason it's the opposite is because what we're doing is we're looking to see where that asymptote crosses the x-axis for the vertical. So if you follow this vertical line here up from where I wrote x equals, if you follow it, you see that this point right here is where it crosses the x-axis. So that means my vertical asymptote would be x equals negative 1. And then I'm going to do the same thing for my y equals asymptote, or my horizontal asymptote. I'm following the asymptote until it crosses the y-axis, and it crosses the y-axis at negative 1. So these are my 2 asymptotes, x equals negative 1 and y equals negative 1. And then before I can figure out all of my transformations, because those help me to determine 2 of them, I need to figure out what my a value is to see if I have a reflection or if I have a stretch or a shrink. So to find your a value, you're going to start at the point where the 2 asymptotes cross, and then you're going to go right 1. You always go right 1, and then you count how many boxes it takes you to get either up or down to the graph. So if I go right 1 and then up 1, it gets me to the graph. So that means my a value is positive 1. And what that tells me is that I don't have any stretch or shrink, and I also don't have a reflection because it's not negative. So as for my transformations, the only 2 things that happened are that my graph shifted down 1 and left 1. And if you remember from the previous problems where we talked about asymptotes, the h and k values are the numbers that you use for your asymptotes. So that means that my h value is negative 1 and my k value is also negative 1. So that's another way you can use those to help you with the transformations. The domain and range are going to be almost the same thing. The only difference, so they're both all real numbers, and then the only difference is that for the domain you say that x cannot equal the asymptote, which is negative 1. And then for range you say y cannot equal the asymptote, which is also negative 1. And then the last thing is end behavior. We're going to have 2 end behavior statements because we're going to talk about as x goes to the right and to the left. And remember that the y statements will both be the same, and they're both going to match whatever your range number is, which is also the same as your y asymptote. So this graph, both of the y values are going to go towards negative 1. All right, for this next example, I want to take a look at the asymptotes first. So my vertical asymptote is x equals negative 2 because that's where it crosses the x-axis. And then my horizontal asymptote is at y equals positive 1 because it crosses the y-axis at positive 1. So I can copy those down. And remember that my x equals asymptote gives you your h value, and your y asymptote gives you your k value. So that's going to help me with my transformations. But before I start writing those down, I want to figure out my a value. So here is the point where the asymptotes cross. You're going to always go one box to the right, and in this case I have to go down 2 boxes till I hit the graph. So my a value for this graph is -2. That tells me 2 transformations. First, it tells me that this graph is reflected, and it also tells me that there's a stretch, a vertical stretch of 2. And then if I look at my h value, that's telling me horizontal or left and right. So this is telling me that the graph is shifted left 2, and then my k value tells me that my graph shifted up 1. So now my domain is all real numbers except x cannot equal -2, because that's the only place in the graph where x will never work. And then my range will be all real numbers except y cannot equal +1. And then my last thing is end behavior. So as x goes towards infinity and -infinity, both of my y values are going to go towards +1. Before we start, I want to write the standard form that we use for the rational family. So what we're given here is an equation, y equals 3 over x, and it tells me that I have 2 asymptotes, x equals 2 and y equals 5. Remember that your asymptotes use h and k, so what this is really giving us is the horizontal shift and the vertical shift. So now all I'm going to do is plug this in. Now my a value from my original is 3, so I'm going to keep that the same. So it's going to be 3 over, and then I'm going to have x minus 2. Remember that you have to switch the sign, so since this is a +2, when you put it in the equation, it's going to be negative. And then plus 5, because your k value does not change signs. For the next one, here's the equation I'm starting with. And then this is going to be my h and k values that I'm going to plug in. So I would have y equals, I'm going to leave the -2, because that was part of the equation I was given. And then I'll have x plus 1, because remember you change the sign, and then -3 at the end. Now in some of the homework problems, all it's going to give you are the transformations, and it's not going to give you the original equation. When it doesn't give you the original equation, you want to use the parent function, which is 1 over x. So if they don't give you a different a value, you're always going to use 1. All right, in order to graph a rational function, the first thing that you always want to do is find the asymptotes. So number 1, you want to do asymptotes, always. So remember that I'm looking for h and k, so my x equals h, y will equal k. Those will be my 2 asymptotes. So my h value is this 5 right here. And remember, you have to do the opposite, so it's going to be x equals -5. And then for my k value, it's going to be whatever, the same sign as whatever k is, so y equals -2. So I'm going to go ahead and put those into my graph. So a vertical line at -5 through the x-axis, and then a horizontal line through -2 on the y-axis. So there's my asymptotes, and that kind of breaks up my graph into 4 sections. And then my graph will be curves in 2 of those 4 sections. So now the next thing that we're going to do, actually before we do the table stuff, we can go through and do domain, range, and end behavior without really even doing much else. So for the domain and the range, it's going to be all real numbers except what your asymptotes equal. So for domain, it's all real numbers except for x equals -5. For range, our exception is y can't equal -2. And then for end behavior, I'm going to have x going towards infinity and -infinity, and both of my y values are going to go towards the y value of the asymptote. So it's going to go towards -2. All right, so now for the table, what I want to show you is what our expectation is going to be. And what we're going to do is we're always going to put where you would get the error, and that's the same place you'll see the vertical asymptote. So since we said that our vertical asymptote is happening at x equals -5, -5 is going to go in the middle of my table. And when you use your calculator, you'll see that you get an error at -5. And you can actually see that I have a screenshot of what it looks like. So over here on the left where I'm putting a purple star, that's what you should type into your calculator. I would not recommend typing it into your calculator as a fraction. So you don't want to type it in the way it looks, how it's typed on the paper. The reason is because if you do that, when you go to your table, all of your values are going to be given to you as fractions instead of decimals. So I think this is the best way to do it. So now I went to the table, and you can see that right here where I'm now drawing 2 purple stars. So that's the table. And you can see I have the -5 highlighted. That's the vertical asymptote. And you see that it tells you that there's an error. So wherever your error is, that should be the middle of your table. And then the number of values that you need to have above or below is going to be told to you by your A number. So remember, A is on the top of your fraction. So in this problem, A equals 1. So what that's telling me is that I have my middle number, and then I want 1 number above it and 1 number below it. So I'm going to go to my table now, and I'm going to use this point here, -6, -3. And then the point below it, -4, -1. So now I'm going to plot these points. I already have the asymptote drawn in. That's where the error was. So now I'm going to do -6, -3, that would be here, and -4, -1 would be here. And now you have just kind of a general idea of what the parent function looks like. So remember, it's going to be the 2 curves. Really, the points are telling you what little sections the curves are going in, and it kind of tells you the stretch of the graph, so if it should be stretched or not. For problem number 2 here, I want to first find the asymptotes. And if you look at the equation, both h and k are 0, so that means both of my asymptotes are 0. And in case it's hard to see, you could rewrite this as -3 over x minus 0 plus 0. So you can actually see the zeros, but remember that when a number is missing, it means that it's a 0. So now we can go ahead and fill in domain and range, because once you know the asymptotes, it tells you what the exceptions are going to be in the domain and range. And then for the end behavior, I still need to have x going towards infinity and -infinity, but both of my y values are going to go towards the y asymptote, or the horizontal asymptote, which is 0. So I'm going to plot those asymptotes on my graph. So this is x equals 0, and then y equals 0 is horizontal. And now we can move on to our table. So in our table, the thing you want in the middle is always your vertical asymptote, or the one where x, your x asymptote. So I want 0 to be in the middle, and I know that is where my calculator is going to give me an error. And if you look here, I have it highlighted on the table. So when you plug this into the calculator, make sure that you type it in as a division problem, not as a proper fraction. And the reason is because if you type it in as an actual fraction, it's going to give you your y values in your table as fractions. So if you want them as decimals, you have to type it in as a division problem. So I have my error on there, and then whatever your a value is, and I know that there's a negative, that tells you that the graph is reflected, but I'm just looking at the number. So I'm looking at the number 3. Since that's our a number, that's how many numbers we need to have on our table above and below the error. So that means that I'm going to go from -3 to +3. So 3 above and 3 below. So I'm going to copy these numbers down. So we have 1, 1.5, and 3, -3, -1.5, and -1. Now we have a lot more, we have 2 more points actually than we usually have. Normally we have 5 points on our table, and on this one we have 7. So because we have extra points, what we're going to do is we're only going to graph the ones that gave us whole numbers. So we're basically going to throw out any decimals. So I'm going to throw out this point right here and this point because they gave me decimals, and I have enough whole numbers that I don't need them. So now I'm going to actually graph this. So I'm going to graph -3, 1. I'm skipping over -2, so I'm going to -1, 3, and then 1, -3, and 3, negative 1. And then these will be enough because you should know what the parent graph looks like, so you know the general shape of the graph. This tells you what sections you're in, and then it also tells you how stretched your graph should be. The asymptotes for this problem, this number here is my h, and the 2 is k. Remember that we take the opposite of the h number, so it's going to be positive 1 for my x asymptote and then positive 2 for y. For domain and range, it's all real numbers except the asymptotes. So x cannot equal 1 for the domain, y cannot equal 2 for the range. And then my end behavior, x goes towards infinity and negative infinity. Both y values are going towards positive 2. So now I'm going to put the asymptotes on. So positive 1 for x, positive 2 for y, and now I go to my table. So again, I have over on the bottom left, I have a screenshot of what you should have typed into your calculator. You have to make sure that you put what is in the denominator in parentheses, otherwise the calculator only thinks that the first thing you typed is in the denominator. So you have to type it in how I have it shown there. And then for our table, we want the vertical asymptote or your x asymptote in the middle. So that would be positive 1, and then, which I show here on the table. And then because our a value is 4, I want 4 numbers above and 4 numbers below. So our table is going to have a total of 9 numbers, but then we're going to throw out any numbers that are decimals. So I'm going to go from negative 3, and then 2, 3, 4, 5. So from negative 3 to 5, that's going to be all the numbers I'm going to copy down. So this is 1.67, 0, negative 2. 1 is the error because that's where the vertical asymptote is. And then 2, 6, 3, 4, 4, 3.3, and 5, 3. So now I'm going to cross out all of the values that gave us decimals, which actually is only 2 of them. So now I'm going to plot all these other whole number points. So I'm going to have negative 3, 1, negative 1, 0, and 0, negative 2. And then asymptote's already drawn in. So now I need 2, 6, 3, 4, and 5, 3. And now I'm going to connect these dots. So I know the general shape of the graph because of the parent function, and then you connect the dots, which tells you which quadrants it's in and also what the stretch looks like.